All right, we're back. We're on page 90 of math analysis, which is a huge accomplishment. If you've gotten to this point, you should feel pretty good about yourself. You've learned a lot of math, and we're going to keep going. So this is hopefully all review. Looking at these problems, these look way more annoying than the last page. So we'll see. It says find the exact value and then find the approximate values. None of these look like they're going to be famous, and that's disappointing. But let's see if we can do, let's just see if we, oh wait, actually the first one might be famous. Let's see. So I'm gonna say that secant squared of 3x minus pi over 2. So we subtract 1 to get 8, divide by 6 to get 4/3. So really, the secant of 3x, this is begging for u substitution. And so one of the advantages of u substitution, hold on, let me not screw this up. Plus or minus 2 over radical 3. One of the things u substitution does for you is it reduces the amount you have to write. Like I wouldn't have to write 3x minus pi over 2 every time if I had just started with u equals 3x minus pi over 2. Do the whole problem from there. But for some reason I didn't do that, so my work's going to be worse. I don't want to solve this problem. I want to solve this problem. So you never flip over an angle. You flip ratios all the time. But like there's not a scenario where you're gonna write the cosine of 1 over 3x minus pi over, like that's insanity. So don't do that. So what do we got here? Cosine plus or minus radical 3 over 2, every quadrant. I know it's a pi over 6, so I know that, let's see what we can do. 3x minus 3 pi over 6. I'm doing that because I know the answers are pi over 6s, so like it's already kind of common denominator type thing, equals, should I do the slick thing maybe, where I do like, so what's the slick thing? It's where, like I could write all 4 of the quadrants, but I know that like these two angles have the same reference angle. So really like I could just do pi over 6 plus pi times n, and that would work. And so it's less writing, so I'm going to do that. So pi over 6 plus pi times n. I sort of generally don't like this, and let me tell you why. The reason I don't really like it is that sine is, I must have lost my voice there, by the way. Sine is so everything sine tangent, whoa, ASTC. Go do something a little weird and you can't remember. I don't like that sine is positive in the first quadrant and negative in the third quadrant, and I'm generalizing both of them in one shot. Like something about that bothers me. It's not wrong. It's just, it bothers me because like, what if only the positive ones work in like some bigger context? So, you know, it's kind of up to you. I'm going to continue to do this thing that I don't really like because I started down that road, but I don't like it. So if I add 3 to the numerator and then I divide by 3, the denominators all just become 18. So I'm going to get 4 pi over 18 plus pi over 3 times n, but also 8 pi over 18 plus pi over 3 times n. I'm going to simplify those. So x is going to be 2 pi over 9 plus pi over 3 times n, and also 4 pi over 9 plus pi over 3 times n. So I think it's better to have 4 answers here. So it's weird, right? Like I'm doing it this way, but I'm saying like I think it'd be better to do it the other way. I'm a hypocrite. I'm not going to go back and fix that. I'm just going to live with that. Let's try the next one. I will check those at the end. This one's, I'm going to go on record as saying definitely not famous. There's no way. Add 7, divide by 2. We get the cosecant of 5x minus pi, which we're just going to end up solving a sine equation, but like, you know, add 7 is 17, divide by 2 is 17 halves. So sine, I always like to solve the sine equation. So what's going to be a problem though is when we check this, I think the calculator will give us cosecants in our answers. And so we're going to have to deal with that. So where is sine positive? Quadrant 1 and quadrant 2. So 5x minus pi could be equal to the inverse sine of 2/17 plus 2 pi n. So that's quadrant 1. Or quadrant 2 is going to be pi minus the inverse sine of 2/17 plus 2 pi n. So we need to add pi. There's not really anything to combine it with, like all that much, and then divide by 5. So should I, I'm going to do it in 2 steps because one of them is a little weird. Pi plus, so I put it in the front, just, I don't have a valid reason for that. Preference, I'm going to add pi. So this one's going to be weird. So here we're going to get 2 pi, because I'm adding pi, minus sine inverse of 2/17 plus 2 pi n. This is inefficient. It's not wrong, it's just inefficient. The reason it's inefficient is if I let n equal -1, it's just going to cancel this out, right? So we could just get rid of that 2 pi. That's just like we already rotated once. We could get rid of it. I'm going to leave it because sometimes when you're solving trig equations, it's not about the most efficient answer. It's about like the easiest to understand. And I think that if we leave it, it's a little easier to understand. But I also think that a lot of you will reduce it out, and that's totally fine. Oh, I forgot that. Get in there. And so this will become, the other thing you can do, I don't know why I break it up into a bunch of things. You could do just 1 fraction plus 2 pi n, and then all over 5. Like both of those are okay. And then n is an element of the integers. So I'm going to check these and then come back in the next video, I think, and finish this off. So let's see what happened. So the first one had famous angles. That's good because I'm pretty confident that the solution the calculator gives will look like the solution that we got. So we're going to solve 6 secant of 3x minus pi over 2 squared plus 1 equals 9 for x, just all reals. So we get, why? You know what I'm going to do? I'm going to try, so you can see it's adding 2 pi over 3 every time, which we definitely did not think it was going to do. Oh, it's adding pi over, why is it adding 2 pi over 3? Oh, because it gave us 4 solutions. We gave only 2, so to get only 2, we added pi over 3. It's giving 4 solutions. You know what we're going to do? We're going to go back to the drawing board here and plug in our answers. Let's do x equals 2 pi over 9. So does this work? And it's supposed to give us 9, so it does work. What if I add pi over 3 to that? It still works. All right, so that means that formula is working. Now if we go here and we do 4 pi over 9, okay, and then if we add pi over 3 here, that works. So we got them. All right, so that worked. That's the annoying thing. Sometimes, and so maybe the answer to why it gives 4 is that the calculator doesn't like the fact that sometimes cosine is positive, sometimes it's negative, like in a given, I don't really know. That's what I think. I don't like when I vary those. Let's see what happens here. I'm not optimistic about the answer to this looking anything like the answer that we got, although I'm confident in our answer. So, and that's a very trig thing. Oh my gosh. Well, no, this looks a little like our answer. So here we have 2 pi minus the inverse sine of 2/17 divided by 5. This is our second answer. This is the calculator combined it. It got rid of that extra 2 pi. Perfect. And then here, what do we have? We have 2 pi over 5, which we had, times n. We have pi over 5, which we had, and we have inverse sine of 2/17 over 5, which we had. It's actually the same answer. I was not optimistic, but the calculator decided to give the same answer. So I'm going to go back to the notes for 1 second, and then I think that we will cut this video here and come back in the next one and finish off these notes, and that's a big deal. So anyway, I will see you in the next one, and we'll get this done. So see you there.